This is the final heat exchanger for Team 2. We are Arion Morshedian, Seena Vafaee, and Lucas Serlin. This is what the device looks like while it's running. As shown, there are no external leaks. When tested, there were also no internal leaks. Attaching our heat exchanger to the test rig is quite simple. As shown, half-inch copper inlet and outlet pipes on our device fit rigidly into the fittings and form a watertight seal. These are the values of the inlet and outlet temperatures of the hot and cold water and the values of the hot and cold water flow rates. This is a parallel plate style heat exchanger. Heat is conducted through aluminum plates that separate layers of hot and cold water flow that are created by acrylic spacers. All of the surfaces are sealed with silicone and clamped shut with a total of 18 quarter 20 fasteners. To manufacture our heat exchanger, first, the 7 spacers that make up the layers of the device were cut out of a 1/8 inch thick sheet of acrylic using the laser cutter. Next, the front and back plates were cut out of a 1/4 inch thick sheet of acrylic, also using the laser cutter. The front plate was then etched with labels to indicate how the pipe should be connected to the test rig and relevant team information. After the acrylic pieces were cut, masking tape was applied to the surface of a 0.032 inch thick sheet of aluminum. Outlines of the aluminum plates that would be used to conduct heat between the layers of the device and the centers of 2 of the holes for the fasteners were cut through the masking tape with the laser cutter. Masking tape was used because the markings did not show up on the aluminum when the laser cutter attempted to etch directly onto the surface of the aluminum sheet. Using the etchings in the masking tape as a guide, a punch was used to clearly mark the centers
Ding.
of the 2 holes on one of the 6 aluminum plates. After using the sheet metal brake to cut out the 6 aluminum plates, all of the plates were clamped together firmly, and 0.255 inch holes were cut through the stack of plates using the drill press at the positions that were marked by the punch. Then, one acrylic spacer was added to the stack. The aluminum plates and the acrylic spacer were fastened together using quarter 20 bolts through the 2 holes. Using the spacer as a template, the rest of the holes were cut through the stack of aluminum. After deburring each hole on every plate to help ensure that the plates would sit flat against the acrylic sheets during the application of the silicone sealant, the assembly process was initiated. First, the thicker front and back plates were glued to spacers using acrylic glue to create the first and final layers of the heat exchanger. 8 partially threaded quarter 20 bolts were placed upright on a table and the base layer was placed onto the bolts. Then, silicone sealant was applied to the bottom of an acrylic spacer. The spacer was assembled onto the stack and more silicone was applied to the top of the spacer. An aluminum sheet was then placed on top of the spacer, and this process was repeated until all the layers were assembled. Next, the copper pipes that were used for attaching the device to the test rig were put in place and joined and sealed using an epoxy. After allowing the sealant and the epoxy to cure overnight, the remainder of the fasteners were put through the remaining holes and tightened in a pattern around the device to prevent uneven application of force to the layers at any point during the assembly. Finally, the surfaces were cleaned a little so that our final product would look more presentable.
There were multiple changes that we made after testing the prototype heat exchanger. There were 2 main goals we had. Number 1 was to reduce the leakage that we saw with the first test, and the second goal was to increase the amount of heat transfer. The leakage was reduced by using better manufacturing processes, so using like a proper jig to ensure that the tolerances were a little bit tighter. We also used more fasteners around the edge to increase the clamping force and used a different method of applying the silicone. In order to increase the heat transfer, we first went from steel to aluminum. The reason we used steel in the first case was because that was what we had on hand, but of course when ordering, aluminum had a better thermal conductivity. We also reduced the thickness between the plates. Again, the acrylic was just what was on hand in the first case, and then we were able to order thinner acrylic to increase the number of layers and increase the overall contact area between the 2 operating fluids. We also had a significantly higher temperature difference between the inlet and outlet of about 10 degrees for both fluids as opposed to 5 degrees with the prototype.
Start prototyping as early as you can. Design is iterative. If you don't leave yourself enough time, you'll find yourself with the prototype as your final heat exchanger. Take immense care when manufacturing. We found it difficult to make a watertight seal, and that manufacturing sloppiness was a primary cause for this. In the same vein, test your heat exchanger before competition so that you have enough time to address any leaks before your official run.